First, do you remember what r equals a sine theta and I cosine theta look like? Okay. Let's go here. What's cosine of 0? 1. Let's do r equals 4 cosine of theta, okay? So 1, so wouldn't you agree that right off the bat, r is at a max, so all the way out here. And then as theta turns, what happens to cosine? As the angle gets bigger and bigger, cosine of those angles get smaller and smaller. Now, if cosine gets smaller, r gets smaller. If r gets smaller, then the distance you travel from the origin gets smaller. So we're going to gradually work into the origin at pi over 2, yeah? And then as we go into this quadrant, r is negative, which means we're going to back up, and that's how we complete a circle. Sine actually starts at 0, and as theta gets bigger, sine gets bigger and bigger, until at pi over 2, sine is at a max, so r is at a max. That's as far out as we're going to go from the origin at any point, and then sine starts to get smaller, so we work back in. Now, that said, not everything is a closed figure. Theta equal r is a figure that spirals out. Theta equal pi over 6, what's that? That's a line, right? So there are a lot of polar figures that aren't closed figures, but there are a lot that are. Now, here's the thing I want you to consider. What would make a closed figure? Why would you get a closed polar graph? Okay, oscillating, because r starts at, let's say we start at the origin. If r starts at 0, then gets bigger and bigger and bigger, but then goes back to 0, then didn't we start at the origin, get further away from the origin, and return to the origin? So what makes a closed shape and polar is the ability of a function, if the function is 0, then bigger, then back to 0. Now, obviously, sine and cosine, those are the best candidates for that. But there are a lot of functions that start at 0, gets bigger and bigger, and then go back to 0, then back to 0. But keep that in mind, because that is a big idea of what we're about to see. Now, these you could say, r equal 4 sine theta. You could actually say that that circle is like a one-petal rose. It's not a very good rose. It doesn't look like a rose at all, if you agree with me, but we'll see. Also, last thing I want you to remember, this is a lot of review. I should have put a review section in. Sine is symmetric at the y-axis, that circle, and cosine is symmetric at the x-axis. The circle is on the x-axis. That was a really quick review, but do you remember all that? All right, cool. Now, today's lesson will involve this guy, this b right there. That is going to change things, because instead of cosine being 1 and then gradually getting 0 and then gradually being -1, everything happens faster. In a much smaller space of angles, we're going to see cosine go to its max and back in, and max and back in. So that'll cause a little different behavior, but for the first time only, let's do a table. At 0, what's cosine? 1, and therefore r is 4, yeah? So we're starting at the max distance from the origin. Let's go to pi over 6 is interesting. What is cosine, 4 cosine of 3 pi over 6, or 4 cosine of pi over 2? 0. So just in this little time frame, cosine went from here to here. Well, does that mean it does this? No, it means in all these angles, r went from 4 to a little less, and a little less, and a little less, and a little less, until it was in here. So no, it didn't just draw a straight line there. It gradually, as the angle turned, the r went smaller and smaller. Now pi over 4 is fine. We could do pi over 4, but it's kind of messy. So we're going to jump to, we're going to go by every pi over 6. So the next is 2 pi over 6 or pi over 3. What is 4 cosine of 3 pi over 3? Negative 4. All right, so be careful here now. Remember your skills. Here's pi over 3, and I'm at the origin facing it, but if it's negative 4, I go back. Now, if you go straight through the origin then, my circles, my graphs are all stretched because of the window on this. Yours are good circles, but mine are. Then you actually end up opposite pi over 3, so here, so like that. Now the next interesting point is 2 pi over 6, 3 pi over 6, or pi over 2. What's 4 cosine of 3 pi over 2? 0. So I'm back to the origin, yay? When I face pi over 2. 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, or 2 pi over 3. What's 4 cosine of 2 pi over 3 times 3? 1 times 4, 4. So here's 2 pi over 3. And do I go forward 4 in that direction or backward 4? Forward is positive, so I go forward 4. At 5 pi over 6, I get cosine of 3 times 5 pi over 6. If the 3 and the 6 cancel, then I get 5 pi over 2. 5 pi over 2 is like pi over 2. What's cosine of pi over 2? 0. So I'm back to the origin. And pi. If you did pi, you get cosine of 3 pi. 3 pi is like pi. Cosine of pi is negative 1, so we get negative 4. So when I face pi, I don't go forward 4, I go backward 4. Now that actually completes the leaf like that. Now if you went, write yourself a note, if you went from pi to 2 pi, you get the same petals on top of those. So if I kept making a table, you'd see it just do that exact same thing. You'd get 6 petals all together, but 3 would lie right on top of the original 3. You down? All right. So looking for trends, 3 theta was 3 petals. So in the next problem, 4 theta will be 4 petals, which of course is absolutely not true.
Wow.
Yeah. Yeah, I misled you. You fell into my little trap. You're going to need 2 columns of tables because this is going to be a lot of points. So here we go. 0 is interesting. What's 2 cosine of 4 times 0? So do you want to keep it scaled by 1 and have it inside the, what's the greatest R you're going to get here? 2. Do you want to keep it small or do you want to change the scale so it's a little bigger? Okay, so let's go by half rings. So we go out to the edge, a half of a unit per, you get that. So at 0, what do you get? R is 2. So I'm starting at the origin. What do you reckon an interesting, if you look back, all the really points we focus on are the maxes and the zeros, the maxes and the zeros. What do you reckon the interesting point that I'm going to get a 0 is? When theta is, let's think of it this way. When would cosine be 0 when you take the cosine of what? Pi over 2. So that means theta would need to be pi over 8. Put in a pi over 8. Pi over 8 would yield 0. Now the question is, where's pi over 8? Well, if here's pi over 4, and pi over 8 is halfway, so right there's a pi over 8. And that's a 0. So we went into the origin really fast. Now because we went into the origin really fast, this is a thinner petal. 2 pi over 8 or pi over 4. When I put pi over 4 in, I get 2 cosine of pi, which is negative 2. So I'm going to actually my third point will be in the third quadrant. Then at 3 pi over 8, I'm just going by pi over 8 each time. 2 cosine of 4 times 3 pi over 8 is 4 times, so 3 pi over 2, and that is 0. Don't overthink it. Use that. I mean, look at the pattern here. You know, it's 2, 0, negative 2, 0, 2, 0, negative 2, 0. So at 3 pi over 8, we're at 0. At 4 pi over 8, or pi over 2, what's the next number in the pattern? 2. So we're going to face pi over 2 and go forward 2. At 5 pi over 8, which is here, right? It's just before that pi over 3 mark, yeah. What's the r? 0. So back to the origin. At 6 pi over 8, or 3 pi over 4, what's r? Negative 2. Now this is, those you be careful again. Now pointing to the second quadrant, but we're backing up, so we end in the fourth quadrant. So we're at the origin, and now we're backing up to the fourth quadrant. That should have been pi over 4. 7 pi over 8. What's the next number in the pattern?
0.
0. And pi. 4 pi is 1. 2 cosine of 4 pi is then 2 times 1. So we're going to go forward 2. So you can see that in here, when I went pi, I got 3 petals. Here, when I went pi, I got, you kind of got 4, right? Because you got 3 and 2 half petals, so you kind of got 4. But the deal is this: when you keep going, here they fell on top of each other. Here they won't. If you go to 9 pi over 8, we left off at 2 here. 9 pi over 8, which is here. Okay, we're past the quadrantal now. We're past 180. Yeah. What is the r? 0. So we were here. We're back to 0. At 10 pi over 8, or 5 pi over 4, negative 2. Yeah. So at 5 pi over 4, we're going to actually back up. So that puts us in the first quadrant. At 11 pi over 8, what's the next number in the pattern? 0. 11 pi over 8 is this ugly guy there. 12 pi over 8, or 3 pi over 2, times 4. The next number is 2, so we're going to go. Did I do something wrong here? Oh. I screwed up. I didn't go back to 0. Okay, so 0, sorry. Then we're going to get, I'm sorry, I just got myself off. 0, 12 pi, we said that was, what did you say it was, 2? 2. Oh, forward 2, I got you. Okay. What about 12 pi over 8? 13 pi over 8? Back to 0. 14 pi over 8, or 7 pi over 4, negative 2, and let's 15 pi over 8. I'm running empty here. Is 0, yeah? And last but not least, 16 pi over 8, or 2 pi, is 2. So 4 theta is not actually 4 petals. It's 8 petals. It's 8 petals. So looking for trends, so we don't have to make this table all the time, which is terrible. We see that if B, and by B I mean the coefficient of theta, if that is odd, or sorry, even, then what do you know about the number of petals? Then there are 2 B petals, or double. But if B is odd, then there are B petals, or the same as B. Okay? What about the A out front again? What does it do? It changes out how far you go. So you can think of it as the length of the petals, the max R. max distance from the origin. Cosine roses. We said cosine circles are symmetric at the x-axis. What about cosine roses? They're symmetric about the x-axis. This is definitely symmetric at the x-axis. This is symmetric all over the place, but it is symmetric at the x-axis. Yeah? Okay. So symmetry at the x-axis. Now, the goal is to use those ideas to just anticipate what the graph would look like, and then you graph. So would you do the first one, please, not by doing a table, but by saying there will be this many petals, and this is how far I'll go. And symmetry. So I have two possibilities, blue and red. Do you agree that we're going to have 4 petals? Okay. They're both symmetric at the x-axis, but only one of them's right. Which one? The blue's right. Why has it got to be the blue? Yeah, it's 0. Cosine is at a max. Cosine max is at 0. This cosine has a petal here. First petal is at the x-axis. So that's how you know it's the blue, not the red. Okay? Speaking of first petal, odd, even is usually pretty darn easy to do, but odd, not so much. So, how many petals here? 5 or 10? Okay, there will be 5 petals. And how will the length be? 8? Okay, so we'll need to scale this by 2 maybe. All right, now, if odd, find the first petal. Now, the first petal is easy. It's at 0 degrees, or right there, yeah? Now, as opposed to the table where they actually get made in a very distinct order, when we do the full rows, we don't need to do them in any order. We can just say how many petals and actually what's the spacing. Now, if it's 360 degrees total and we're dividing it among, it's evenly spaced, they're evenly spaced. Divided by the number of petals, then what's the space between each petal? 72 degrees between petals, yeah? So if the first one is 0, the second one is at 72, where is that in reference to the referencing? Past. What's this one? What is it? Sorry, I mean degrees. 60 degrees, okay? The reason I'm using degrees is because I don't reckon you have any idea. 2 pi over 5 radians doesn't mean much to you. So I'm going to go into degrees for a second, okay? So 72 degrees is going to be over here, yeah? But the minute you have 1 petal with symmetry, you have 2. There's got to be 1 here also. All right? Now, if I kept going with the 72, 0 to 72, 72 to 144. Where's 144 in reference to the reference angles? Between 135 and 150, yeah, in here somewhere? And again, with symmetry, and they should be evenly spaced and symmetric at the x-axis. You with me? Okay, it is important sometimes that you remember that table, because if they don't have you graph the whole thing, then you have to know the order in which points are made. In a case like this, it might be helpful to verify with a table or with some table points. I know that this would want to do something like 1, 2, 3, 4, this is not the order, 5, 6, 7, 8. I know it's going to want to have 8 petals, yeah? But I'm not going to get the whole thing, so you need to kind of know, all right, where does it get made? We definitely know it starts at 0, right? When would it be 0? This would come into 0 every, or it would be, remember it goes 1, 0, negative 1, 0. This would go between those by gaps of pi over 8, all right? So this is how I would do this. I would say, all right, at pi over 8, 0. At pi over 4, negative. At 3 pi over 8, 0. At 4 pi over 8, positive. At 5 pi over 8, 0. At 6 pi over 8, negative. At 7 pi over 8, 0. And at pi, forward. So as far as the pedals, we would only get that kind of 3 plus 2 halves kind of situation. You ready? All right, I know I gave you one below that, but let's skip that and actually, it's important. You try it. Okay, try the next one, please. I don't have it in my slides. Imagine every pi over 6 would be interesting. So pi over 6, pi over 3, and pi over 2 really should get you everything you need. So are you getting something like this? Okay. All right. Let's go to sine. Sine's a little more complicated, but not a lot more complicated. The problem with sine is the first pedal is not as easily located. Cosine's first pedal is right away, it's 0. You're starting. But sine, not so much. So you should start by saying, how do you find the first pedal of a sine rose? A pedal, a max, a pedal, actually, let's write it this way. The big idea is a pedal tip is when the trig is at a max. Okay, you're getting a pedal tip because ours is good, as big as it's going to be. You're going out as far as you can. And you're going out as far as you can because the trig is as big as it can be. So for sine, you should say, when is the b theta equal to, well, what's sine max at? Pi over 2, okay? So you're going to find the first pedal by saying, well, when does the argument of the sine come out to be pi over 2? That's where my first pedal is. So here, I would get my first pedal when 3 theta comes out to be pi over 2, which means I get a first pedal at theta equal pi over 6. When I hit pi over 6 and I put that in, 3 pi over 6 is pi over 2, I get a max. So 1, 2, 3, 4, my first pedal is here. Now, rather than unwrap this in order with a table, let's do spacing, okay? We know that there will be 3 pedals, yeah? Or will there be 6 pedals? It's 3, okay? What's the spacing? In degrees. 120, yeah? So if the first one's at 30, then the next one is 150, and the next one is 270. So we're going to have there. When we did circles, sine was symmetric at the y-axis. Is this symmetric at the y-axis? It is. Sine is symmetric at the y-axis. I didn't say the positive y-axis. It actually goes back and forth between positive and negative. 3 theta is symmetric at the negative y-axis. 5 theta is symmetric at the positive y-axis. 7 theta is symmetric at the negative y-axis. It goes back and forth, bounces like that. You'll see later. Sine symmetric at the y-axis, though, is the key. But be careful, because there's a lot of ways to get that symmetry. You know here that this is how many petals? 8 petals, yeah? Let's find the first. Would you find the first petal for me? Where is it? Either in degrees or radians, whatever. Pi over 8, okay? We said pi over 8 is here-ish, just below 30 degrees, you know, like 7 degrees less. I'm changing my scale if you don't mind, so it's bigger here. Notice the 2. Okay, what's the spacing? Maybe degrees now. 45. So if the first one is 22.5, the next one will be 67.5. And with symmetry across the y-axis, won't those have to be copied over here, yeah? So that leaves me off, that kind of leaves me off, but if you keep going 40, it's 45 degrees between petals, yeah? So 45 degrees would put me just shy there. There's another pi over 8. And here's a pi over 8. And here's a pi over 8. And here's a pi over 8. 8 petals, we? Okay, is that symmetric at the y-axis, even though it's not on the y-axis? Yeah, it's symmetrical at the y-axis. Okay, that said, try 4 sine 2 theta on your own. Is that about what yours looks like? Kind of an X shape? All right, cool. 5 theta. Where's the first petal? This one's a little harder here. 5 pi, let's use degrees. 5 theta equals 90 is where our first petal is, yeah? So where's the first? 18 degrees. 18 degrees would be in here somewhere, yeah? And by symmetry, there'd be a copy over here. What's the spacing? 360 divided by 5 is 72. So if I start with 18 and I go 72, where's the second? 90. 90, go 72, that's 162. Not that I know where 162 is, but then go 72 from there, that's 234. 234. So here's 210, here's 225, here's 240. So 234 is in here between the pi over 4 and the pi over 3. And symmetry. Are they evenly spaced, or is yours evenly spaced? Should be close. Okay, I think I'm going to call it at that. We're not going to, this is not in the homework. This actually isn't until 129, but it's too much at once in the book, so I'd try and teach it a little early, but I'll touch on it this one. No big deal. So here's the deal. Surely we're not going to get through questions, but I do need to get caught up. So this is what I want you to do. If you get out 107, sorry, 108 and 109, and tell me what questions do you have or not understand, I will work them, or I don't know, would it be better to work them and just do my key, or would it be better to record me doing them and put that? I just need to get caught up. Just a key, or record me getting you started? Okay, just a key. All right, cool. These are the problems that 5th period already asked about. So if you have something besides those that you'd like me to put up this weekend, let me know. Yes?
Set 108, number 13.
14, did you say? Okay.
108, can you do all 22?
All of 22, yes. 5 on 108. 5 on 108. Yeah, okay. Did you say 20 on 109? Okay. Let me know if there's anything else. 23. Okay. Okay, so that's part of your homework, actually. I will work those and put them up this weekend. So go over your mistakes, and we're going to start. Yes? 15109? All right. Let me know if there's anything else, or if you just want to put on the board, that's fine too. And we're good.